Try to make the topic a little different, which is on one of the application of these harmonic light sources in trying to understand quantum materials. And again, I'm not a material scientist myself. We're laser tool developers, and then try to see what are the unique applications we can access with the harmonics. And so this work depends on a lot of collaborations with Kaiserslautern, NIST, Uppsala, and Kiel, and funding from NSF and DOE at the Moore Foundation. And this is a more extensive list of collaborators. The students are listed here, and I'll mention their names when I talk about their work, but Tom Silva's group are experts in magnetic materials, as are Peter O'Neill's group, who's expert in the theory of magnetic materials. Stefan and Martin and Hans Schneider are also experts in quantum materials, magnetic materials. We get samples from UCSD. We've worked with Michael Bauer a lot in photo emission. Roger and Wayland made the nano samples, so we could look at transport in nanostructured systems. And then Klaus is another collaborator in the area of magnetic materials. So I talked this morning about the light source. So now talk about one of the applications, but I did want to mention that anything you can use a laser for, you can use high harmonics for, and you get higher spatial resolution, higher temporal resolution, and higher phase and more sensitive phase information, just because the wavelength of the light is much shorter than the wavelength of visible light. And in addition then, we also get to do things like photo emission, since the single photon photo emission, since for example, the 29th harmonic of Thai sapphire is at a photon energy of about 42 eV, well above the work function of any material. So you get beautiful photoelectron spectra using harmonics. And in fact, this is one of the killer apps. I won't talk very much about it, but it is one of the killer apps because it is the one application where we always have too much high harmonic flux. Because if you shine the X-ray beam on the sample and you want to look at the photoelectron spectrum of the material, if you pull too many electrons off, and we heard Linda talk about this, you distort the spectrum. So in fact, what you want for photo emission is very high repetition rate, 50 to 100 kilohertz, and very small energy per pulse, and that gives the nicest photoelectron spectra. And of course, because we have time resolution also, essentially it lets you map the whole band structure of the material, because it can probe all the way out to the Brillouin zone edge, which you can't do with ultraviolet or visible light. So you see the whole band structure of the material, and for some of these strange materials like the topological insulators, or these materials that undergo very fast state changes, if you can see both the band center and the band edge, you can actually learn a little bit more about the physics. So that's one killer app. Another killer app that I talk about tomorrow is in imaging. And I'll wait till tomorrow to talk about that. But what I'll talk about today is these, what we can learn about magnetic materials. And the nice thing, of course, about these high harmonics and ultrafast X-rays in general, that small things like electrons can do things on very fast time scales. And what X-rays do for you, which that a visible ultrafast laser cannot, is it can penetrate through thick samples, like a magnetic material. It's not opaque. It's not transparent to visible light. You have these are the X-ray absorption edges of three magnetic materials, iron, cobalt, and nickel. They have these characteristic absorption edges, both in the extreme ultraviolet, around 50 eV, and also those are the M shell absorption edges, and also in the soft X-ray, these are the L shell absorption edges, and there's nice magnetic contrast at either edge. And so currently we're doing all our work at these M shell absorption edges that are very easy to reach with high harmonics. If you add in imaging, then you can image at the wavelength limit in 3D. And Dr. talked about this, and of course harmonics are fast enough to capture even the non-equilibrium electrodynamics, because electron-electron collision times in solids are in order of a femtosecond or less, depending on the material, and so one can easily visualize how the non-equilibrium electron distributions move around. So this is the sort of thing, for example, quantum materials are of interest because they have very strong correlations. So if you've got these funny charge density wave materials where there's such strong electron-electron interactions that you can have charge ordering, and then at higher temperatures you get a metallic phase and an insulating phase. And sometimes in these materials it's hard to know, why is it an insulator? You might expect it to be a metal, and by essentially, plotting the material with a femtosecond laser and then looking at the band structure using photoelectron spectroscopy, you can learn and measuring the response time. If it responds on a 10 femtosecond time scale, you know that there has to be dominated by electron-electron correlations. But if it responds on a 200 femtosecond time scale, you know that that's a time scale corresponding to the lattice vibrations in a material. So even simple experiments that just, pluck the material and watching how it relaxes tells you something about the interactions. And if you think it's bad in a charge density wave material, then when you add in spins, there is no microscopic model of magnets on short time scales. There isn't even agreement on how you would make the model. Which was very surprising to me, because I thought magnetism has been around for centuries, and I knew that superconductivity was not understood, but even something like a simple 3D Burr magnet is not understood, because it's such a, because if you excite it with a femtosecond laser, you have an out of equilibrium electron distribution, and you've got the same excited state problems that Linda was talking about for the clusters and molecular charge transfer systems. But we have this great tool because we know we can probe the charge or the spin state, and because we've got a comb, we can do that at multiple sites. So if you're looking for correlations, it's a great tool. And I think it was Paul mentioned, turn something bad into something good. So with harmonics, people would say, but you've got all the colors. Wouldn't it be much nicer to just put all the harmonics in one and get something nice and bright? But here for spectroscopy, we can use the fact that we've got a harmonic that overlaps the iron edge, the nickel edge, and all these other magnetic edges, so we can look at how they're behaving, and if I were able to learn something by being able to look at the two atomic sites at the same time. And of course, if you're interested in screening, exchange, and dynamic quantum coherence, then it's also a great tool to look at that. But this is something we're trying to see if we're actually seeing. I won't talk about it because I don't know enough, but it's sort of, we're beginning to see hints of this in our experiment. But the thing I like the most is that, we learn from theory, we compare with it, and then sort of try to close the loop so we can try and understand how these materials are working. So I talked about motivating why we're interested in magnetic materials, and just from an interesting application point of view, there was some beautiful work done by Theo Racing in the Netherlands, where he found he could take a gadolinium alloy and shine a circularly polarized laser pulse, even one pulse, onto the material, and the material would flip its magnetic state just with one pulse. And you could write it back and flip it back and forth. And so this, of course, is of great interest because this is, a very nice and all-optical magnetic switching. It's not as fast as the pulse, but it's still faster than any other approach, and people still don't know. That was beautiful work done in 2007, and the physical mechanisms for this behavior are still not understood. Due to just challenges in theory and experiment. So with the harmonics, we can look at these magnetic states at multiple sites, try to identify the microscopic mechanisms, and this is just fundamental work that can inform future technologies like spintronics and data storage technologies. So, just as a brief introduction to the work, the timescales of magnetism span from the very long, but for a long time it was not understood that they also span to very short timescales, because people thought that the fastest timescales were on order of nanoseconds, which are the precessional motion of the magnetic moment. But then, just about 20 years ago, Jean-Yves Biget's group did an experiment where they shone a femtosecond laser on a magnetic material, and the material demagnetized in, you can see it, this is 5 picoseconds, so it demagnetizes in about 100 femtoseconds. I know people had it was a big surprise to everybody. Big surprise, because that can't be explained by a precessional motion. That's way too slow. So what's going on? Well, we know when you heat a metal with a femtosecond laser that initially you're going to get some lumpy distribution of the electrons, because you're taking electrons from below the Fermi level in the metal to above the Fermi level, and then they need to collide, thermalize, and establish a hot Fermi Dirac. So the electron temperature, because the heat capacity is so much smaller than the lattice, the electron temperature can spike well above the Curie temperature while the lattice stays effectively cold. So you do not melt the lattice, but you can still drive the electron back well above the Curie temperature, and then the spin is randomized. And so, but the question is how? And that is 20 years, and we still don't know why. How, exactly how. So there's, and of course it's a complex system. You've got, you've got electron-electron scattering, electron-electron spin flip scattering, electron-magnon scattering, electron-phonon scattering. There's spin transport. There's the exchange. Energy moves around. The exchange spinning changes. And so this is impossible to model at a microscopic level. But to sort of try to give one example of how we can shed light on the mechanism, and of course what you try and do with these measurements is try to separate the timescales, just like in molecular systems. You've got charge transfer is fast, and then electron motions are always faster than vibrational motions. Similarly, in a magnetic system, you think about the femtosecond laser heating the electron back. They somehow or other scatter the spins, then they couple to the phonons, couple to photons, and then you try and model this. It's usually modeled phenomenologically, but and even this is only from relatively recent, and already we know this is not completely correct because it doesn't take into account that you can have spin motions. But to try to make a long story short, okay, so this is the phenomenological 3-temperature model that I told you about. So if you notice here, so after the femtosecond laser pulse, your electron temperature spikes up to well above the Curie temperature in a normal ferromagnet, because their heat capacity is so much lower. And then coupling to the lattice will very slowly heat the lattice, but the lattice stays well below melting. And then this is the spin temperature is a little bit phenomenological, but microscopically.
Is this experiment?
This
curve. Yeah.
No, that is a phenomenological 3-temperature model with a lot of fudge factors, because that's what. But it does model the experiment.
It almost looks like the experiment.
So that you could measure the lattice temperature.
Okay.
You could measure the electron temperature, but you can't measure the spin temperature. It's a bit of a non-physical thing.
Right.
But it represents the magnetic state. Isn't that right? So you can measure this, and that's well known just from gold, silver. It was, back when I was a grad student, people didn't quite understand this perfectly, but that was figured out in the 90s. But when you add in spin, it's not known. And I'm oversimplifying, and I can tell you who you should invite if you want to learn more about these materials. But as an experimentalist, I'm going to oversimplify 2 theoretical models that we were able to distinguish between with harmonics. So the first model was proposed by Bert Koopmans. And so what he said is, okay, so you've got to add in some exchange splitting when you've got a magnetic material. So, okay, you heat your electron, the electron scatters with another electron, it can split its spin, and then cool. And of course that would, you know, in this situation, you are flipping a spin. So of course, this local scattering would give rise to a reduction in the magnetic moment, so you would see the material lose its magnetic state. Then a few years afterwards, Peter Oppenair proposed, said that's not what's happening at all. It's not this local spin flip scattering. What happens is you've got majority and minority spins in the material, but their scattering lengths are not the same. If their scattering length, and that's known, if their scattering lengths are not the same, then the spin ups can travel a lot further before they scatter, whereas the spin downs scatter almost immediately. So now you have this spin polarized current that goes out of the region you're probing, but there's always a return cold current, but that's not spin polarized. So it would look like the material demagnetized, whereas what happened is that you had a whole lot of spin polarized electrons rush out of the probed region. And of course this is a non-local mechanism, and this is a local mechanism, so we figured, well, maybe we can see the difference between these two mechanisms by doing an experiment. And so just to sort of show, this is my cartoon, experimentalist cartoon, that one mechanism was you heat the material and you had local scattering, and then the other one, you heat the material, a spin polarized current, a hot current leaves the region and your return current is cold. And so those are very different. So how can we read the magnetic state and try and see, yes?
I'm sorry, but I don't still understand what is spin temperature. I mean, it's not physical. Okay,
No, and you're not the only one. And I'm not the only one either. You know, this, we've been on hours-long phone conference calls trying to, when we're writing up any of these, you know, it's not well done. So, okay, we can all, well actually, can I answer it in another few view graphs? And you'll see why I'm struggling, okay? It has a concept, you know, that if you heat a magnetic material towards its Curie temperature, you're going to have relaxation, you know, some randomization of the spins, so the magnetic moment will decrease. So statically at any temperature, you can define you can define the magnetic state. Is that right? The problem is in a dynamic situation, your spin temperature doesn't really mean a lot because everything is changing and interacting, and you've got scattering and transport and everything. And so spin temperature doesn't really have physical meaning, but you can use it to describe the level of magnetization in the material. Just like, you know, how do you define the temperature of an electron bath? You know, you look at your Fermi-Dirac, you look at your slope at the Fermi level, and you can fit that to an electron temperature. But if you have a non-equilibrium electron temperature where you take part of the electrons from below the Fermi level and just put them way up, you can't define the temperature there. So it's the same problem. Does that make sense? If you have non-equilibrium distributions, you can't define the temperature.
Yes, so why do people call it temperature, but they can't?
Because they have to talk about it, yes. So this is, yeah. So this is, there's two different phenomenological models, and they don't agree with each other, and there's this is why this field is so much fun. Yeah. So how do we measure the magnetic state? So we can't use the L shell. We can make harmonics there, but at too low a repetition rate to make good measurements. So instead we use the M shell. And if you reflect from, so we can, okay, this is the L shell here, and this is the M shell 3P, for example, in iron. And so we're promoting, when we irradiate, we're measuring either the transmission or the reflection corresponding to these transitions. And if you look here at our harmonic spectrum in the extreme ultraviolet region, you can see that very nicely we can overlap with nickel, cobalt, iron, manganese, ruthenium, and chromium, all at the same time. So the experimental setup is very simple. We send most of the laser beam through a waveguide to make a harmonic cone, and then the rest we keep to heat the magnetic material, which, and we have some Helmholtz coil that allow us to change the orientation of the magnetic moment. So we heat the sample, we look at the change in reflectivity of the sample as the magnetization changes, because this is the magneto-optic Kerr effect in the extreme ultraviolet region of the spectrum, and so the reflectivity or transmission of the sample depends on its magnetic moment. So if it changes, if it decreases, you see a change in reflectivity or transmission. And it is by far the biggest, one of the biggest signals we see in any experiment we do. It's a huge effect that the depolarized reflectivity is dependent on the magnetic state, and you get a huge change in reflection. For example, this is the harmonic spectrum, and the dashed and the solid is the spectrum as we flip the current in the Helmholtz coils. So you can see it by eye. There's a huge change. That's called the magnetic asymmetry, that there's a different reflection depending on what way the magnetization in the sample is. And so, and this is the difference of this, the purple curve is the difference between these two signals normalized, and so we call that the normalized magnetic asymmetry. And if you heat the material, for example, if you heated it up using a heater, you did it statically, then the magnetic moment would be gone, and so you would see there would be no difference between the activity, and this magnetic asymmetry would be flat. So we just look at how the magnetic asymmetry changes. And then the nice thing is we can make multi-layers with different materials, and if this is about 10 nanometer total, we can still probe down through the different metals, so we can read out the magnetic state. And we can, with our MIST colleagues, we can have the two magnetic materials either parallel or anti-parallel, and see if there's a difference in the behavior in both cases. Clearly, if all was happening was spin scattering, we wouldn't really see a lot of difference in these two cases. But if there's spins moving between the layers, we should see a difference if the magnetic moments are aligned parallel or anti-parallel. So that was the experiment. So we take our magnetic multilayer, heat all of the multilayer with a femtosecond laser, and then read out what is the magnetic, or how fast the magnetic state in the nickel and iron change. And the magnetization in the nickel layer decreased, which is what we expected, as opposed to if you heat it up, if you heat the electrons above the Curie temperature, you're supposed to see the magnetization disappear. But what was surprising to us was that the magnetization in iron increased above its normally maximum value. And there's no way you can explain that if spins are not moving between nickel and iron, because there's nothing, we weren't doing anything to increase the magnetic moment in iron. And as luck would have it, it agreed perfectly with Peter Oppenhier's theory that the spins should move between one layer and the other, and of course they have to move down because they can't go up, so they can reflect off the top. And so that's why there's such a strong spin current, and that's why the magnetization in iron increases so much. But fortunately, Chanda Lavarakia was writing his PhD thesis, and so we caught it just on time before we submitted the paper that we said maybe we should do a control experiment. A second set, we had already done several, but we did one more, which was instead of having a spin conductor that would let the spins flow from nickel to iron, let's put in a spin, an insulator. So this is the data I just showed you, if you allow the spins to move between the two layers. But what if you put a spin scatterer or an insulator that won't allow any current? And the insulator is sort of the nail in the coffin, because if you put an insulator and do not allow any spin currents between these two layers, both materials demagnetize. So then Now the only way to explain this is if you can also have local spin scattering within each layer, because the spins can't go anywhere, but they still demagnetize. So that, the nice thing about this is that they were both right, and when you analyze the data, they're equally important, which was, we liked because we didn't want to, you know, it's nicer to prove two people right than to prove one person wrong. And then I talked a little bit about these, you know, part of the charge density wave materials, and this was a collaboration led by Michael Bauer and Stefan Matthias, and we helped them with the harmonic sources to do photo emission, to just see if you take one of these materials that has a charge density wave order, like you can sort of see it best here, where the electron-electron interactions are strong enough that the lattice, you know, it goes from, it goes into these pairwise, the lattice period doubles, and the electron distribution localizes, and that's an insulating state. And in many of these materials, whether they're an excitonic or a MOT or a Paris insulator, why they are is not well understood. So we just did a very simple experiment, you know, again, do the same thing, shine a femtosecond laser on the material and look at how the material responds. And we did that for different materials, and essentially we did it at low fluence and high fluence, and it's easier to see. The photo emission folks love these spectra, and it took me ages to be able to see what they were seeing in it, but the lineouts help a little. So the idea is, depending on how quickly the material responds, you know if it's dominated by electron-electron interactions or electron-phonon interactions. So if the material, if the charge density wave order melts in less than 20 femtoseconds, then since a phonon period and LO phonon period is about 100 femtoseconds, that tells you that this must be a MOT or excitonic. And if, as you change the laser intensity, if the time scale doesn't change, then you know it has to be MOT. Whereas if you increase the laser intensity and it goes from the charge density wave melting time goes from 77 to 44 femtoseconds, that's indicating that there's electron squeezing effects, and that tells you it must be an excitonic state. And then if it's long and doesn't change as you change the laser fluence, then you can say it's predominantly pyros. So this is a very simple classification, and it's, I could say more, but maybe we'll keep it for the discussions.
Margaret?
Yes,
What is an excitonic insulator?
Oh, it's this, where interactions between so when you get this period doubling, so the lowest energy state is when the electrons are localized and the position of the atoms changes slightly to enable this localization. And again, it's electron-electron screening effects are high to have this happen. And it's a little bit more involved, but just to show you that as we got better with harmonics and were able to control their bandwidth, we could get much higher quality data and sort of see exactly where the electrons, we could see exactly how the band structure was changing, and come up, this is not published, but just come up with these, we could actually see that when you put electrons very high in the band, and then the state in the material, the band gap, the band gap in the material started to undergo periodic oscillations, then a lot of things started to happen that had been previously looked at. This was very common back in the 80s. People would look at all of these impact ionization mechanisms. And what's different in these materials is that because when you perturb them, the charge order state can start, oscillating. That you get this sort of it's sort of a runaway phenomenon that as the band gap closes, you can have more impact ionization that puts more electrons up in the band, enhances